We're now ready to learn the substitution rule. The substitution rule is going to help us when we have more complicated integrands as we're trying to integrate. So for example, if we had this integrand, we've got the function 2x multiplied by the square root of the quantity 4 plus x squared dx. Now this is going to be more involved because we're trying to think of an antiderivative. Let's think a minute about differentiation. Here we have the product of two functions, 2x and the square root of 4 plus x squared. Well, if we had that and we were trying to differentiate, not integrate, that would involve the product rule. So as we're trying to go backwards and think of antiderivatives, if we had product rules, quotient rules, chain rules, things like that, it's going to be a little harder to go backwards. So the substitution rule is going to help us particularly when the chain rule was involved. So in order to think about that, let's first of all rewrite this. I'm going to rewrite the radical as a rational exponent. So I'm going to have that quantity to the 1/2 power. And then we're going to think about what happens when we differentiate. I'm going to take the kind of more complicated function here, the radical. Now we know if we had been taking a derivative and we got this piece, there would have been 1 higher power. So this would have been 4 plus x squared to the 1 higher power, and this would have been 3/2, but we need the reciprocal of that power. But then what's the other thing coming into play here? Well, the chain rule would have been involved, and we would have needed to multiply by the derivative of this stuff. Well, the derivative of this stuff is 2x. Oh, wait a minute, we've got this 2x there. I can see from this that this would have been 4 plus x squared to the 3/2 and then this 2/3 power. And that would give me exactly this when I take a derivative. Let's go ahead and just do it real quickly to confirm. So we would move power out in front and those would cancel, and so we'd have 4 plus x squared, decrease the power by 1 to the 1/2 multiplied by the derivative of what's inside, and that's exactly what we had here. So we can do this by thinking like we just did here, but it's a little bit complex, and so we're going to do a substitution that will then help us to figure out what that piece for the chain rule would need to be, and do we have it there or do we need to kind of doctor up the function to get it. So let's see how this works in general, and then we'll do some examples. When you differentiate a composite function, you've got the chain rule involved. You have the derivative of the outer function, and we're going to call that f of g of x, but then you've got to multiply by the derivative of what's inside. If you looked at this and you were trying to integrate this, you need to be able to get back to this function, and this came from the chain rule. So when we integrate, we need to set it up so we have this composite function and we have the piece we needed that would have come from the chain rule, and then we would get the antiderivative here of this function, and then of course plus our constant of integration. So what we're actually going to do is we're going to call this inner function u, and we're going to express this as f of u, and we need this piece to be our derivative of u. And we can replace our dx, and we need to figure out, if we find du dx and figure out what that is, then we can express in terms of du. So if that was g prime of x, then we could express du as g prime of x dx. And so we could replace the g prime of x dx with the du, and then we could integrate, and we would just need to do the antiderivative of this function. Our last step would be, we have a function of u here, but we wanted a function of x, and we know that u equals g of x, and so we would want to resubstitute so that we could get this in terms of x. So substitution is essentially so we can run the chain rule backwards. If u equals g of x is a differentiable function whose range is in the interval I and f is continuous on I, then we can take the integral of f of g of x and having the g prime of x dx and replace it with the integral f of u du. So to evaluate this integral, we are going to substitute u for the g of x, and du is going to be g prime of x dx, so that we now have this integral. Then we're going to integrate with respect to u, and then after we get that solution, we're going to replace the u by g of x. We need to see several examples so we can see exactly how to do this. So here we have a function that we are trying to integrate, and if we look at this exponent here's derivative involves an x squared. So I'm going to identify a u, which is a function inside of this e to the x, I'm going to identify that as x to the third. If I did the derivative, that's going to be 3x squared dx. So I'm just taking a derivative here. And so if I wanted to write this as e to the u, I need to change these in terms of u as well, and du is 3x squared dx. Well, looking here, I have the x squared dx part, but I don't have the 3. So what I'm going to do is divide both sides by 3, and now I know that I can replace x squared dx with 1/3 du. So I'm going to put the 1/3 out in front and the du right here, because we know we can always move constants out in front and multiply those later. So now I have 1/3, and I'm integrating e to the u, and we know the integral of e to the u is e to the u. And then we have plus a constant. So now our last step will be to get this back in terms of x. So I have 1/3 e, replace the u with x to the third plus c. Now, it's not a bad idea to check things. I could check this by taking the derivative of this, and I should get this piece right here that I was integrating. So if I took the derivative, I would have 1/3. The derivative of e to the x cubed is e to the x cubed, and then chain rule multiplied by the derivative of x cubed, which is 3x squared. And then, of course, the derivative of a constant is 0. Well, we can see these 3's would cancel, and indeed I would get this integrand right here. Let's look at another one. It's always good to express radicals as rational exponents. So I'm going to express this like this. And then my function inside of another function, I have a square root function, and inside of that I have 4t minus 1. And so that's what I'm going to call my u. That would mean my du is going to be 4 dt. Now, looking to see what I have here, I don't have a 4, I do have a dt. So I am going to divide both sides by 4 so that I know that dt equals 1/4 du. Now I'm ready to do the u substitution. All of this was u, so that is now u to the 1/2, and dt is 1/4 du. So I'm going to put the du right here, and I'm going to put the 1/4 out in front of the integral. Let's go ahead and do that. That is going to be 1 higher power, which would have been 3/2, but I need the reciprocal of the power out in front, and then plus a constant. This looks like 2's will reduce here, and so I have 1/6. Now I'm going to go back and write this in terms of x, and I'm also going to write this in radical form. So my u is 4t minus 1. That's going to be to the third power plus a constant. Now we could leave it like this. We could also go ahead and there's 3 of these here, and if we were square rooting, then we could bring out and get one of these out in front, and then it would leave us one of these still under plus a constant. Looking at another example, I can see that I'm integrating a function that has a function inside, so a composite function. I'm going to take the inside function, that's 7 theta plus 5. So my du would be 7 d theta. Well, I see that I have the d theta, but I don't have the 7, so I'm going to divide both sides by 7, and I can replace d theta with 1/7 du. So here I have cosine, and this is my u. I replace d theta with 1/7 du, and I'm going to go ahead and put the 1/7 out in front. So I have 1/7 doing an antiderivative here. That would be sine u, and then plus a constant. Now I would want to go ahead and replace the u, get it back in terms of theta. So final answer, I'd have 1/7 sine of 7 theta plus 5 plus a constant. Another example, it looks like here I have an x squared inside of a natural log, but the derivative of x squared is 2x, and I don't have a 2x because x is in the denominator. So I'm actually going to pull a different trick first. I am going to use the third property of logs and move this 2 out in front. And so when I do that, now I see that essentially I have this is 1 over x, and that's the derivative of natural log. So that's a clue for me to say, well, let's let u be the natural log of x. So when I take du, that's going to be 1 over x dx. And Nicely enough, I have that. So that part is going to be my du. So as I do my substitution, this 2 is just a constant, so I will put it out in front. My natural log of x becomes u, and my 1 over x dx becomes du. So we got this down to a very simple thing to integrate. And in fact, I'm going to look at my 2 out in front and say, you know, I could just make this a u squared, because if I take the derivative, I bring the 2 out in front, decrease the power by 1, and that's exactly what I have. And then I need plus my constant. Finally, then getting it back in terms of x, our u was ln x, so this is ln of x, the quantity squared, plus a constant. So what if we have a definite integral and we're doing a substitution? First, you could use the substitution rule to find an antiderivative, capital F, and then you could get it back in terms of x and use the fundamental theorem. So basically, even though we have a definite integral, you could go over and do an indefinite integral with u substitution, get that integral worked, and then resubstitute for x, and then go ahead and evaluate. The other option you have is once you've changed variables from x to u, you can also change the limits of integration and complete the integration leaving it in terms of u. So if you had let u equal g of x, the lower limit, x equals a, would be replaced by whatever we get when we put that a in this function that equals u. So g of a would give us the lower limit, and g of b would give us the upper limit. So sometimes it's easier to just write it as an indefinite integral, go ahead and get it worked, resubstitute, and then go ahead and use the fundamental theorem to evaluate. But sometimes it's easier to get it in terms of u and leave it in terms of u by changing the limits of integration and expressing those in terms of u as well. So we do have a substitution rule for definite integrals if we're choosing to do option number 2. And essentially we let our g of x be u, and this becomes our du, and then we take that u, and if we evaluate it at a, we have g of a for our lower limit, and evaluated at b, we have g of b for our upper limit.